is crack tip opening displacement. So that basically means if you can measure the crack tip open, for example, at the beginning is this tip, but once you stretch the sample and eventually there is some crack tip opening, which you have a blunting area due to the plastic zone effect, and you can measure this displacement called delta here. So that's the crack tip opening displacement, like I told you before, a British method, okay? And American method here is using a much more rigorous way. I mean, is from a mathematical derivation to get you this answer, which is you take any kind of a contour line like this, and there must be a closed contour line, so like the red curve I drew, okay? So by integrate the energy along this contour line, you can actually get this potential energy, and then using the definition of energy release rate, so you can work out the J. The J value is equal to G if it is a linear elastic material, okay? If not, then just using this general equation. So these two can be equivalent by a yield strength. So J equal to sigma ys times the delta. So you can find this is the one you measure from the CTOD, and this is the J from this integral method. The only thing you can link them is using the yield strengths, okay? So first of all, just to introduce how to measure this crack tip opening displacement. And for most of the time, you actually can calculate them by some equation. So because there's a crack blunting here, and you have this crack opening displacement delta. How to get that value? So first of all, let's look at the plastic zone, which is like a circular shape we derived before, and we have found like the actual answer for the for the plastic zone RP, okay? RP is the one we derived, which is equal to 2RY here. This is from the elastic prediction, and this is considering the stress redistribution, and so that is the actual plastic zone. So if you think about the circumference, I mean the whole length along the circumference is 2 pi times the radius, which is ry, which is equal to pi rp, okay? This is like a diameter. So when you open the crack tip, basically you can imagine originally the point is at the center here. Now it's stretched to a point like here and here, okay? So that is kind of the thing we call it delta, the crack tip opening. And how to get that? Because we know strain at the boundary, which is here. You can think this is like a string, but it's a curved string. Once you stretch it, okay, basically it will starting from that point and move further to here and to here. So basically you can work out the strain. Think like you stretch a spring or just a rope. So there is a strain developed, which we call epsilon y. Epsilon y is equal to the stress, which because we know the maximum stress it can reach is the yield stress. So sigma y over E. Or here, if you haven't reached the yield point, then this is just the elastic stress, sigma y. Okay? So basically, you know the strain and you know the original length, which is the one we calculate the circumference, which is pi rp. So basically, the change of the length equal to the strain turn to the original length. Okay, that's the definition of strain. Give you the answer of delta. So let me work out that for you. So delta is the pi rp, which is this one, the original length times the strain. So that is the opening displacement. And it's more interesting to find the relationship of this one with something we know, okay? So first of all, just to give you the RP, we derived that before, which is a function of the stress intensity factor over the yield strength. That is the equation. And if you actually plug in, so basically plug in RP inside this equation, okay, and plug in the strain is equal to sigma y over E. So now let's expand the equation. So first term pi is there. This term is RP, okay, which is here. And the final term is the strain, epsilon y. And you can combine these two by cancel some of the term out, okay? Here you will cancel. So basically I cancel the pi. And I take this part at the front and keep this form here. And if we further reduce that, we will cancel this sigma ys, and we will have one sigma ys left. And then, if you remember the relationship between G and the Ki, which is this one. So it is good to recap you of the knowledge you learned for linear elastic material, okay? So here we still assume this is a small confined zone here, okay? So you can actually reduce the equation into this one, okay? G is the Griffiths energy release rate, and you can finally find the equation like I write before. Similarly, J, which we will derive similarly later on. So you find J just equal to G, okay? The right hand side is the same. Okay, let's move on. So someone also developed this kind of if you don't know this word, is basically the strip yield model, okay, which assume the plastic zone is like this shape, okay, and then you found actually you will derive the same result as before. It's essentially the same result, okay. And in the experiment, basically you do a 3-point bending test, and you apply load from here, and you will actually measure the crack tip opening displacement by attach either like a kind of a clip gauge that's a bit hard, or using a camera. You can using your camera just to visualize how your crack tip opening. So then you can measure that delta as the kind of a measure of nonlinear solid, okay? Okay, let's move on, okay? So the other way to derive that is using the J. So before I go like dive into the J integral, we just recap you this kind of idea for the energy method. So for a linear elastic solid, you remember if you plot a load displacement curve, so for example, for a linear material, it's a linear line, this one. After a crack extension of dA, okay, a crack will move to somewhere here of dA, and then there's a amount of energy released, okay, because essentially you apply a load, this load will reduce, and displacement control, okay. So you are comparing the same displacement here, and you found the energy released is equal to the G times the surface area. Assume there's a unit thickness plate B equal to 1. Okay, so that is the area here. Similarly, for non-linear solid, so you have a non-linear behavior like that curve. And after crack extension, then you also have this energy released. So now we assume J here times dA equal to that energy. So it's just a very similar approach, energy method. And you will find when the crack extends, the strain energy U, if you look at the original energy U, which is, let's just draw the original U, is this whole area. Let's put some mark here, A, B, okay? So original energy, let's say, is OAB, that area. And after the crack extension, then that is minus, okay? That is U O C B, okay? That area, your integrated area underneath the curve, okay? That gives you the change of the strain energy. But most of the time we do the other way. So you'll find actually we're comparing the strain energy after the crack extension to the original one. So you do the other way, which normally, so UOCB minus UOAB equal to DU. So you find this value is smaller than 0, right? It's kind of this area is smaller than the original area. Similarly for the walk, external walk. If you look at external walk is something like this whole square. Originally is this whole square, and now it's become like this smaller square, okay? So that gives you the idea what happens after the crack at once. Is the strain energy and the external walk will all be reduced. So now we move to the J integral. I think that's the most beautiful equation in this elastic plastic fracture mechanics. So it's purely actually at the beginning from mathematics. Okay, this guy James Rice. Okay, he's still alive. So fortunately, you probably can see him in some conference. James Rice, who is from Harvard University, shows that nonlinear elastic release rate J could be written as a path-independent line integral. Okay, I couldn't understand at the beginning as well. So that's totally out of the earth. I think at the beginning I thought there's something very new to me. But when you go to the problem step by step, you will understand why it works. Okay, so this guy, okay, James Rice, I think he's probably the most famous guy in the mechanics field at this moment. Seems like, similar like Griffiths. Griffiths has died, okay, for G. So this guy J integral for James. So that's the link between these two terms. And so the idea behind that is quite simple, is just use this equation. If you can work out the change of your potential energy and divide that by dA, the crack surface area, and then you get this release rate for nonlinear solid. Suppose you have a very small amount of material at the crack tip, okay, and this could be just small area of that plastic zone. So out of the material, the outside exterior surface, I mean that small area, you apply some surface traction. Traction is basically force per unit area, okay? That's like a stress, but with a it's like a vector, like we have learned that at the very beginning. So that is like a force per unit area, and then you have this contour line at the boundary for the whole volume. So now the whole volume for this area is A prime, okay? So we will try to understand that later on, but that is just a terminology for the problem, okay? Let's just come back to understand if you want to derive J, what kind of things you need to do. So first of all is this potential energy. That's the key things. So potential energy, if you remember, is equal to the strain energy minus W, the external work. And suppose you have a kind of a bar and you apply a load uniaxially. So then if you look at a small amount of material, like just like a unit element inside the material, so how much strain energy it can store? So that's some questions we answered before. For linear elastic material, basically you have the stress strain curve behave linearly like this curve. So the strain energy per unit volume, so for that small amount of material, is equal to this area, okay, which we can call this is omega. So that is the strain energy stored per unit volume. We can also call it strain energy density. Okay, and if you look at this area, is equal to half of the rectangle area. So just this the triangle area, half times sigma times epsilon. And if you want to work out the total strain energy of the whole body, like this bar, then you need to integrate that small amount of material over the whole volume. That's why we normally write it as an integral, which is integral over the whole volume times the strain energy density times the small amount of volume. So that's the definition. So for a plate, for example, the thickness B equal to 1. So you can assume that a unit thickness. And then the whole volume becomes like a whole surface area you're looking at. So this shade area. So that's why I write this equation into integration of the surface area, but still using this strain energy density times the small amount of material dA, okay, dA. And now we finish the strain energy. We know how to get the strain energy. The other part is the external work, okay. External work equal to the integral over the force times the displacement, okay. So we're not looking at the stress strain curve. We just look at the force displacement curve. that will give us for a constant force, most of the time the constant force, that was this external work. And for this case, you can see we are apply a constant load on the cross-section area, like here. But what happens if you apply a force on a unit thickness? So you kind of shrink this thickness B equal to 1. Okay, so think about just like a 2D problem. Now you apply a force per unit area on this amount of line. So basically, you kind of if you look at 2D problem, you apply your load on that line. So that's why now the line comes in this problem. So we can rewrite this equation in terms of a surface amount of a surface area. Okay, so in terms of the integration, now we do the integration along that integral. So you can assume that that is the surface, but now it become a line, or this curved line. So you can do this integration on the whole path, okay, like the path we draw before, which we denote here, gamma or something. And the T is basically the force per unit area, is a traction, times the small amount of line, which is here, okay? The T for is defined here. S is the displacement along the curved line. So basically, the reason we do it because the curved shape doesn't necessarily means the displacement is the uniform. So you need actually do the integration by doing all small amount of ds, okay, to get the whole external work. Okay, so this tau I think should be that kind of like a cross-section area, but it become a cross-section line where your load is applied on that line. So now we can get two things. One is the external work in this part. One is the strain energy in this part. Or look at a 2D problem, more like just look at a plate. So now we can almost have this idea to derive this equation. We get this part, and we just need to divide dA. Seems very simple. So let's just work about something more detailed, which, because you find these two integrals, one is over the surface, one is over the boundary line. So that is very different scenario. How can you combine them actually? So this is more like strain energy, the material stored internally, internal energy, and this external work where you define your load on the boundary. Okay, sorry for my writing. This pen is really very bad. Okay, so let's just move on. Just using that knowledge we get. Same problem. Now just derive that more in detail to connect these two integral. So the problem is still the same. We are in a form of closed contour gamma here, and we define this omega as the strain energy density, T as the traction vector, and Ui is the displacement vectors along that traction Ui. Okay, and the ds you can see actually is just a small amount of ds. You can think about a small amount of line here. along the boundary. And that is a displacement along that as well. You can link them later on. I will show you. So now if you assume this small amount of material have completely fractured, so the crack will from this point and travel and eventually fracture sample. So now you can think about after the fracture, the total amount of strain energy will equal to 0, right? So for the fully cracked surface area of dA, which we define here, let's work out the change of strain energy, which is du, change of strain energy, equal to the final state, 0, minus the initial state, okay? So let's work out the initial state. And let me write that down. So now it's become minus A W is still the same. Consider a small amount of area dA is equal to dx. Sorry, so this should be dy and dx. So that's give you the dA, dx, and dy. But now, if we look at the integration, we are doing the integration over the all area, although this is still a small area. So that's essentially we are equal to the dA here. dx now can be substituted by dA because we fracture them all. So now we can substitute that into this small part, which is equal to minus again over the whole surface area W times dA dy. Okay, dA now is more like constant. We can take it out to the front. So now the question is how to link this surface integral to the line integral so that we can combine them together. So let's look at that small amount of line. What the relationship between this? Let's draw that. Assume is a linear line as a small line, not this bit, probably even smaller, ds. Okay, about here. This is a linear line. Now we want to find a relationship between ds and dy, which is this vertical line, and horizontal line, which is called dx. We don't care about that, okay? We don't worry about that. And now we can actually find dy is equal to ds times this angle is sine theta, right? It's just like this is a triangle. Using that longest line, you can times sine theta, which you get the dy. But now there's a relationship for the vector, which is a normal vector. You can decompose that. One is nx here. The other one is ny. So n actually can be written as nx, ny as a vector. And nx is sine theta. If you look at the theta, the relationship geometrically, you will find nx is sine theta, which the theta can be here, okay? Is equal to this angle, sine theta, and is cosine theta. So now you can simplify dy is equal to nx times ds. So that's the simple trick, actually, how we can relate the dy to ds. So let me finish that. So we can take out minus dA in front and integral here, A prime, and W is still the same. Now we write dy equal to this term, which is x dx. Okay, question. So let me come out. Did you update the slides? Yes, I think I updated the slides for this one, but you should focus on the one I'm talking about now. And it's not going to be tested, of course. It's too hard even for me, but not that hard. Look at the detail. Okay, it's just some simple trick you need to use. Okay, let's carry on. We finish up the change of the strain energy du equal to this part, and now the mistake I have made is here. It should probably you will also make this mistake. So this part should be changed because now we changed the dy to ds. So the integral from should be changed to the line integral as well, to along the whole boundary line. Okay, so that's the correct. And now we move to what called the external work, the change of external work dw, which again is after the fracture, there's no external work, 0. Okay, minus the original external work, you apply this force or surface traction, and it's T here. And there's some trick here again, is just to think about how to change the Ti is the same, but now I want to change this delta U to something related to the coordinate system X. So which we can do actually is we can write this, I will explain that, delta Ui over delta X times dA times d. Okay, so why it looks like that? So actually we actually doing the trick like this. So delta Ui, you can think about is a gradient of delta I due to the partial derivative of x. That the gradient of the displacement along the x direction times the displacement, for example, dx along that direction times dy. Since we have a crack dA, now we can change that to dA. Okay, so these things, if you cancel them out, you will become this times that. Okay, I mean here should be a dA in front. Sorry, ds. So here there's no y here. It should be just ds. Sorry. Okay. So now actually this become very similar. We are all doing the integral along the line, on the contour line ds, and the only thing different is the part inside of this integral. So let me summarize that. And I just want to delete some of the things here so you can see clearly. Oh, I just move a bit up. Okay. Very messy, but you will have a much clean version in the next slide. But basically the same approach. So now, if you remember, the potential energy is equal to the strain energy minus the external work. So basically, you put this term minus that term. Okay. Remember, there's a minus sign in front of them. So basically, in the end, there's a minus sign here. I should put it here. This is wrong. So minus sign here. Put a bracket. Okay. So you will get this term minus that with a minus in front of it. And now you find they all do the integral along the line, ds. You can take the common things together, w or omega ns, and this ti term together, and divide the dA to the left. So that gives you minus the potential energy dA, okay? Equal to this line integral, which you combine this common term omega ns and also the ti, this partial u partial x, and times the small amount of ds here. So that is the answer for J integral. J equal to these things and equal to that, right? Now you actually get this answer. I think it's not that hard if you follow the approach. I kind of prepare you about all this energy method, and the only trick probably is here, where you change the dy, and so that you can remove the surface integral into, I think it's change the surface integral to the line integral here. So finally you combine the line integral together, which give you that. So what that tells us, so this is the clean version for this derivation. You don't need to remember that, just understand that would be enough. So the physical meaning, I mean, the usefulness for that integral is demonstrated by another great guy, Hutchinson. They're all from Harvard. Hutchinson, Rice, and these three people, they show J integral uniquely characterize the crack tip stress and strain in the nonlinear material. Okay, that will give you the unique solution. Okay, John Hutchinson. Okay, that's another good guy still alive. So they demonstrate that first of all you can use this equation, okay, for linear solid, and that is J is equivalent to G in linear solid. You can think about it as an energy parameter, but also a stress intensity parameter because of this equation. But more importantly, they derive these things, which is called path independent rule for the J integral. So the people will ask, if I choose a different contour line, will I get different answer? The answer is no, you will get the same answer. So no matter where you choose your contour line, even a bit close or a bit further, the derive, the J, once you do that line integral, okay, ds, you will get the same answer, exact same answer. So that will be very useful. So you will actually find, you can choose any of the line to do the integral, and you can choose even from here, from the outside to here, and you need to go through the crack and to here. You will still get the same answer like that, okay? So that's the usefulness for the J integral. And the relationship between the CTOD, the crack tip opening displacement delta, is related with the J, while the yield strength, as I mentioned before, okay? So you will probably ask, how can I use the J in our experiments? How will we measure that value if you give me a piece of material? So in the lab, you can actually attach some strain gauge on your specimen, but that looks very inefficient. But there's now a digital image coloration system. Basically, you put two cameras to look at the specimen under tension. Okay, you have a two camera to look at, and then you can generate this strain map, basically like a virtual strain gauge. So you can get the strain points here, and you can use the finite element to help you to do the integration. You get the J. That's a very tedious method. Actually, it's not that practical most of the time. But with the DIC, it gets a bit easier, but still not that good. You need sometimes using both experiment and the finite element to do the calculation. But there is another simple approach, which we call the JIC test, just the test the fraction toughness of nonlinear solid without using the integral. That's kind of a contradict with our answer, our derivation, but it's still using the idea of integral, but you in some way you cancel that out. So basically you're doing a 3-point bending. And let me have a look of how much time I have. This is another derivation. I don't want to go through that. I think I just want to explain the idea behind that. Okay. So quickly, just a 3-point bending test on a kind of a notched specimen. So for this kind of nonlinear solid, we will get this solution, which is more like a load displacement curve, but now it's a moment over the rotation angle curve, which will also give the strain energy. So here you will find M can be a function of the B. B is the distance here, okay? W minus A. A is the crack length, times a function of theta. That's just an assumption here, but it's valid. When you do the derivative of B, you'll find you'll cancel that out. You will get this minus delta A. So strain energy, again, you can integrate this curve to get this shade area. External work is the M times theta, like first times the displacement. And potential energy, similarly, this minus that. So when you use the J definition, not the integral definition, it's just the energy definition over A, you will find that you can change the derivation over A by replacing that to B. So which is essentially do the derivation on the B. So basically you substitute AM equal to B squared G theta. You will sorry, should be this equation. You do the derivation, you will cancel that, and then B squared will become 2B here, and the G theta will still stay here. And then you will find, actually interestingly, this whole term, what it looks like actually is the whole term can be substituted by think about G theta is equal to M over B squared. Okay, think about like rearrange that equation to here, and you substitute that, so become 2B, this one, and I change that to M theta D theta. Interestingly, these things is exactly the strain energy you derived, right? So this part can be substituted by the strain energy. Okay. So J is simplified. J equal to 2 over B times the strain energy. Very simplified. And in the experiment, we found it's very hard to apply a moment on the sample. Its equivalent method is just apply the 3-point bending just by a point force like that, like we normally do, and you will get the similar curve like that. And actually, the strain energy derived from the moments is equal to derived from the displacement. So that could be equal. So that's the way we normally do, is we get the strain energy not from the moments theta relationship. We get from the load displacement, which is much easier to measure. So in the experiment, we just need to measure the force displacement and also measure the crack length, A, dA, crack extension. And now we get that from experiment, and we use this formula, which is just one unknown, U, okay? So B is that crack, the safe material without crack, B. So using that, actually, in your experiment, you just apply your load until you get some crack here. And then that's the initial crack, without crack, sorry. That's the crack initiation point without crack. And then you have a crack growth, delta A2, which will give you this potential energy, U. So here should be U, okay? So at each crack extension, you get a J. So for example, for this term, it's J2 to be U2. So U2 is from that integration, okay? That gives you the U2 at crack extension of delta A2. So by doing different integration of different crack lengths, you have this R curve. So that is R curve as well, but it's more called J delta A curve. Is R curve for nonlinear solid. Okay. So that's how you can simplify the J integral into a much easier way to do your experiment. That's all for the elastic plastic fracture mechanics. I think it is a bit overwhelmed in the kind of equation or derivation, but overall, if you look at the approach or the background, is still using this equation. Okay, so that's the only thing probably you need to remember for kind of this kind of theory. Okay, that's all.